welcome to this morning session of our conference. It's a pleasure to introduce you to Professor Guillermo Elicabe from the Universidade Nacional de Mar del Plata. And Professor Elicabe is the director of the INTEMA, which is the Institute of Technology of Materials at the University of Mar del Plata in Argentina, which is a unit of CONICET, which is more like the CNRS in France. Professor Guillermo Elicabe has been working for a long time on light propagation and radiation in transparent and semi-transparent media, and a very good friend, a long-time collaborator. It's a great pleasure to have you here, Guillermo. Please.
Well, thank you very much. Good morning, everyone. First of all, I would like to thank the organizers of this meeting for inviting me to come to Rio once more and to meet old friends and to visit again this beautiful city. The work I'm going to present has been done in collaboration with all the people that appears there. They are all from INTEMA. INTEMA is, as Elisha said, it's an institute of research in material science that depends on CONICET, our National Research Council, and University Nacional of Mar del Plata. The work I'm going to present is about thermal parameter identification in remote heating. Actually, I'm going to be more focused on some of the topics related to this subject. First of all, what motivated my work, the work I'm going to present today? I would say three small topics are related that merge together to give place to the work I'm going to present today. The topics were diffusion of light, scattering and absorption by small particles, and self-healing of polymers. They were all developed by different people. In diffusion of light, I worked with Professor Orlande for several years, co-directing, co-supervising Bernard Lamien, who worked in state estimation in hyperthermia treatment of cancer induced by near-infrared diode laser heating. And also with Guido Baez, he's a PhD student at the University of Tandil in Argentina, who is still finishing his PhD in subject optical tomography for detection of foreign bodies in live tissues. That's what is related to diffusion of light. Scattering and absorption by small particles was a theme I developed for several years. Is where I have my first choice. Self-healing of polymers was developed by a group of people at INTEMA. They deal with designing polymers that have the property of self-healing. So merging all these topics together gave rise to what I'm going to present this morning. What's the self-healing of polymers? Imagine that we have a damaged piece. There's a piece of polymer that has a damage inside. The damage is inside of the piece, so you cannot access to it to repair it directly. You want to repair it by some remote operation. The idea is that this polymer has been designed in order to have the properties, chemical properties, that make it reparable by adding heat to the place where the damage is present. So the idea is to reach the place where the damage is present by some type of radiation that is going to localize in the place where the damage is present. This technique can be used for with other purposes like local phase separation and localized reactions. This is going to be the framework around which we are going to develop the next slides. As I said before, we have done work in relation to self-healing of polymers by developing materials that have the property of self-healing. That is, materials that, by the addition of heat in a right amount, you may make the material return to the original condition. This is work done by some of the people of the group of polymers at Intema. At that moment, they are not preoccupied about how the heat reaches the place where the damage is present, but they are focused on designing polymers that have the property. There is work in the literature where by adding nanoparticles, gold nanoparticles, you may be capable of directing or concentrating the radiation that I was showing you before at the point where the damage is present. So that's what I'm going to expose next. This is the idea of the problem. This is the scope. We have a sample of polymer, that is the one that is the parallelepiped over there, that is thin in one direction and has two other dimensions that are larger. The sample of polymer is transparent to the radiation and is loaded with gold nanoparticles. The load of nanoparticles is evenly distributed and is in a very small amount. So it doesn't change the properties of the material, and it doesn't change any of the visual properties of the materials either. The idea is to hit the sample with a beam of light that comes from a laser at a given frequency, and to check the temperature. The idea of the presentation I'm giving today is to analyze how the temperature at the point where it is marked there evolves with time. Light traverses the sample and leaves on the other face by enters the sample as a collimated light and leaves as diffuse light. Inside, two things happen. One is light is absorbed by the particles, by the nanoparticles, the gold nanoparticles. Part of the light is absorbed, and part of the light is scattered. And later on, light leaves the sample. So I'm going to go over here. So let's see how is that this thing happens. Let's assume that we have a particle like the one I put there, like with a rod-like form. That particle is in the way of a laser beam that's going to a detector. If we put and remove the particle, the amount of energy captured by the particle is proportional to its cross-section. That's something very intuitive. It's like the concept we have of a shadow. So you put the particle, you intercept a fraction of the light that is incident into the detector that is proportional to the cross-sectional area of the particle. If you remove it, all the light goes to the detector. What happens when you have a gold nanoparticle? A gold nanoparticle has particular characteristics that make that the light that goes to the particle is like taken by the particle in a larger amount than its cross-sectional area. So it takes more light than it's intuitively or normally for a regular particle to take. So it captures light, and that light that it captures is going to transform in heat. It's going to be absorbed by the particle and transformed in heat. So that makes the gold nanoparticles very efficient. The efficiency is related to the material. It's not only gold, it may also be silver and platinum, those called the noble materials, the noble metals. And it's not only the material. If you put a big particle there, it's not going to have this reaction. So it has to be small, very small, in the order of the nanometers. So if you have a gold nanoparticle, that's going to happen with the field lines of electric field. They are going to converge into the particle, and the particle is going to be very efficient in absorbing light. So if you put a small amount of particles in a matrix, let's say in this case a polymer matrix, those particles are going to take most of the incident light, and you don't need to put many particles. So you have this advantage. The amount of energy absorbed by the particle and later released as heat can be easily calculated using light scattering theories. So you have essentially the efficiency, absorption efficiency that is dependent on the radius of the particle and the refractive indices. So it's the size, as I mentioned before, and the optical characteristics of the material. Also on the wavelength of the incident light. This efficiency multiplied times pi, the radius square, and the density of energy that we are imposing to the particle may let you calculate the amount of energy that is absorbed by the nanoparticle and that is released as heat immediately. These are the characteristics of gold. These are the characteristics of 3 different materials. This is the optical characteristics in bulk. You have the refractive indices. K is the imaginary part, N is the real part of different materials. In red, you see the ones of gold that may not look particularly different than the rest. But if you transform this into efficiency, you have that gold has, at this wavelength that is around 500 nanometers, have an efficiency that is around 20 to 30 times larger than a similar particle of the same size made of cadmium selenide or aluminum alloy. So that shows clearly, numerically, how this effect of high efficiency is represented. So with this in mind, we are going to do a model of the setup I showed you before. So we are going to model how, the idea is to model how the sample of polymer loaded with gold nanoparticles and irradiated with a laser light is how that sample, how the thermal process goes on. That is, what is the map of temperatures around the particle, around the sample. So we do it in 2 ways. First, we have to model the optical part. That is how the radiation reaches the different points of the sample and how that radiation transforms into heat. So here we have the configuration. We are going to do it in 1 dimension. We're going to use the radiative transfer equation. That is the one over there. This is in the diffuse approximation and 1-dimensional. We have all these parameters involved. This is the radius of, I'm going to start showing you typical values. This is the radius of the particles we are going to use, 6.5 nanometers. This is the wavelength of the incident light. This wavelength coincides with what they call the resonance plasmon of gold. These are the refractive indices, real and imaginary part, of gold. This is the refractive index of the polymer matrix. And these are the efficiencies that we calculated. As you see, the system is mainly absorptive because the scattering efficiency is very low. And these are the number of particles per cubic meter. And this is the fraction of particles. If you can see at the end, the fraction of particles, this is the volume fraction of particles, is very small. So you have very little particles occupying just a very small part of the volume in a typical application. So this equation has been solved by other authors under this setup. Essentially, we have a dimension that is C. We are going to model only this dimension. This is the thickness of the sample. We are going to make some assumptions that I'm going to tell you in a few moments. Finally, the idea is to calculate the heat flux inside the sample as a function of C. This is like a normalized theta. This heat flux is the heat flux times that heat flux time the absorption cross section, that is this quantity, gives you the amount of heat release per cubic meter. The amount of heat released per cubic meter in this piece of polymer. So this is the heat transfer configuration. So as I said, we are going to solve how the temperatures distribute along the sample. The idea is to start with a sample at a given temperature, to apply the light, and then to resolve the heat transfer equation in principle in 3 dimensions. We are imposing convective boundary conditions on the 6 faces of the slab. And this is the amount that links the heat transfer equation with the radiative transfer equation. This amount, this quantity, that gives you the watts per cubic meter that are released by the action of the laser on the particles inside the sample, is given by this quantity. This quantity varies along the theta direction, as it shows here. This is a normalized quantity, but it's more or less proportional to U3 prime. And this is what they call normally the heat source in the heat transfer equation. Here we have some typical values we're going to use in the next slides to run the simulations. The assumption here is important because it makes possible to solve this problem without coupling it. So we just solve the radiative part, and then we include it into the heat transfer part. And the assumption is that only the nanoparticles that are located in intersection of the beam and the sample become heat sources, not others, because we assume that away from this area, from this volume, light is not important. The amount of light that is traveling through the sample is not important, because most of the light is going to pass because of the particular absorptive characteristics of the system that we have put together. So only the light that goes into this area is going to affect the nanoparticles there, and those are the only ones that are going to produce heat. The reality is a little bit different because there is light that goes from this place to places that are out of the volume, and that light is going to hit particles that are going to produce heat also. But we are going to neglect that, and we are going to show that the approximation is good with some experimental examples. So with this idea in mind, I go back to the experimental setup. The idea is to do some simulations I'm going to show you with different configurations of this experimental setup. Essentially, it's the same I showed you before. The parameters we're going to use are the ones I showed you before, and these are the thermal parameters that are going to be needed for solving the heat transfer equation. So we did some simulations using this setup for different configurations in the illumination. So we kept all the variables and parameters the same, but we changed the type of illumination we applied to the sample. Let's see some of them, and then I will pass to the estimation part. So we define the cases depending on the type of stimulation or type of illumination we apply to the polymer sample. Here is a case in which the illumination, this is the typical sample we're going to use. It's a sample of size, it's a square sample in the XY dimension. It has a thickness of 2 millimeters, and is illuminated with a density of light of 0.0175 watts per square millimeter, and located in the center of the sample. And the form of the form of the spot is a square. Is not very, the size. The form is not very important. So this is the result of the simulation at different times, from 0 to the end to the final time that is around 350 seconds. This is the evolution of temperature in the center of the sample, the exact center. That means it's the center in the 3 dimensions. And this is the evolution of, as I said, the evolution of the map of temperatures in that center for zeta equal to 1 millimeter. That is in the middle of the zeta dimension. So as you can see, the temperatures evolve increasingly as time goes by. We have prepared several examples with different illuminations. Essentially, we changed the size of the illumination. We kept the density, and that made that the total power incident onto the sample also change. That gives place to different final temperatures at the end of the experiment. The experiment takes from 0 to 350 seconds. And this is how the light, how temperature evolves inside the sample. So remember that our objective was to focus the light into a place and to produce heat in a confined region. So we analyzed several configurations with the idea of what? The idea is to check the model in 3 dimensions, but also to develop some alternatives to the 3-dimensional model. That is something I'm going to explain later, but this is going to help to check the alternative models. Well, as you can see here, we are putting into play more energy, and then the final temperature is higher than the higher temperature in the previous examples. We have also this. And finally, example E, in which the shape of the spot, the light spot, is more elongated, and it also is going to have other consequences. As a summary of what I showed before, these are the evolution of temperature for each case. The cases are the ones that are here. As you see, temperature evolves in a different way depending on how you illuminate the sample, and reaches temperatures that are quite different. We also analyze, so those were the experiments run. These were the experiments run in a simulated way, but we also run a couple of experimental examples. We build the polymer. We include the nanoparticles. So we made what we call a nanocomposite. It's a composite material made of polymer, transparent, and gold nanoparticles in a very small quantity. You don't realize that they are there, not visually, and they don't change the properties, the mechanical properties of the material. The sample dimension in this case was larger than the ones I presented earlier. And the form of the light spot is also different. This is probably more realistic, because normally the spot of a laser beam is circular. This is the temperature evolution that we actually measure in the center of the sample. This is a second experiment in which we have a different polymer. We have also different nanoparticles. The polymer in this case is an epoxy polymer. And the nanoparticles I'm going to show you later that are much smaller than the ones of the first experimental example. The evolution of temperature is like the one shown here. This was measured in the laboratory. And it reaches about the same temperature, but in a much less time than before. Something that is interesting to see is how the heat source distribution for each case is. As you see, this is a normalized plot. The optical parameters in experiment 2, the one that I showed you before, are the following. And the difference with respect to the experiment 1 is the size of the nanoparticles. As you see, you have 6.5, the radius of, in this case, and 1 nanometer in this other case. And also the concentration of nanoparticles is different in each case. As you see, you may have different heat sources distribution depending on how you design and choose the values of essentially the size of the nanoparticles and the amount of them in the material. You may have a very steep curve that shows how the heat is released as you move into the sample in the dimension for one case and for the other. In conclusion, the program analyzed has several parameters and inputs that can be modified to produce different results on the output variables. That is, it has a great flexibility. You have many parameters that can be accessed easily and modified to obtain different setups and different conditions to apply this technique of reaching a place with heat confined in a given area, in a given volume. parameter estimation, state estimation, optimization, and control can be performed on the system with different objectives. That's something I'm not going to talk about much today, but it's something that we have in mind to keep working with this system. What I would like to explore now is about model reduction. We know that model reduction may be necessary in some cases, essentially when you have to deal with online data, or even when you have to deal with offline data and you have problems that take too much time computationally. So model reduction is something that one always would like to be able to do, and we'll try to explore some of the possibilities that can be assessed here. In this case, I'm going to present some model reduction related to obtained by reducing the dimensionality of the problem. So you may do model reduction in different ways, but the one that I'm proposing here is just by reducing the dimensionality of the problem. Model reduction is tested by analyzing how the 1- and 2-dimensional heat transfer models behave with respect to the 3-dimensional one. That is, you have the 3-dimensional one, you assume that is the right solution, and you try to see how the 1-dimensional and 2-dimensional models may be used to represent the exact and right solution. Well, the analysis is going to be performed using the outputs of the system to estimate its parameters. So the idea is we're going to use the output of the 3D models to estimate parameters using the 1D and 2D models. One is going to expect some mismatch in the parameters estimated, depending on how well the conditions of 1-dimensionality or 2-dimensionality are obtained. So the test is performed not only in terms of how much the state variables in the reduced models follow the real ones, but also on how the model parameters are close to the real parameters. To do so, the model parameters are estimated for the different reduced models using data from the full models to check the validity of the approximation. Well, later on, I will show some alternatives that may be useful to improve the way in which the reduced models see the parameters. So, ¿cómo te tiempo? 6 minutes. Mm-hmm. Well, what I want to show you is just one case. Because I'm running out of time. Let's take the case in which the illumination is in this elongated form as a rectangle. You have here. This is the map of temperature, and this is the temperature in the center of the sample. What we do is the following: we generate the data using the 3D model. We add noise to it, and then we come with first the 3D model and estimate the parameters. That's something that is quite obvious. The parameters are going to be okay. They're going to be estimated correctly. And the mismatch is going to be related to the noise in the data. So you have the noise in the data that transformed into a mismatch in the value of the parameters with respect to the real parameters. That happens when you use the 3D model to estimate the parameters. I mean, I take the data from the 3D model and I estimate the parameters using a 3D model, something that quite obviously is going to give you good results, and the only mismatch is going to be related to the noise in the data. If we go further, you may want to estimate, using the data generated with the 3D model, the parameters using the 2D model. So the 2D model, in this case, takes 2 dimensions. One is this dimension, and the other one is the thickness. And it neglects the dimension that is in this direction. That's the one in which the sample is more homogeneous because we are illuminated in this direction, and this is probably what we may think that is infinite in extension as compared to the thickness of the sample. In this case, we have a pretty reasonable conversions to values that are close to the real ones, as you see. Values that are close. So we may say that a model that in 2 dimensions is a good candidate to estimate parameters from real data and to have these parameters converge to values that are quite close to the real ones. So we have done this with all the cases, but because I have little time, I want to go directly to a case in which we have even improved more the behavior of one of the reduced models. We have added to the measurement I mentioned before. We have added 2 more measurements at different places into the sample. The places are in a cross section of the sample, in the middle of it, and in the middle of the thickness. That is 1, 2, 3. These are the places where we measure. We measure the three quantities, temperatures. In the center, we have the measurements we have before, and on the sides, we have these 2 measurements that, of course, give you smaller values. And we are going to use these generated values using the 3D model to estimate parameters. The parameters estimated using this configuration are much better than the ones that we obtained before, not only for a 3D model, that is something that is obvious, but also for the 2D model. As you see, the error is around 5%. Well, I would like to go directly to the experimental examples. We have checked our model using the experimental examples. In this case, the example I showed you before, we call it experiment 1. We have measured 2 thermal parameters, like they are the heat capacity and heat transfer coefficient. These 2 parameters are the ones that are supposed to be unknown. Actually, they are unknown here, although we have measured them independently. We would like to see how they, what are the values that, when you put them into the model, that means how can we adjust the temperature values using the heat transfer equation, how the parameters converge to some parameters. And this is what we obtained. For the first case, we obtained, this is the blue one is the experimental, the red is the theoretical, is the estimated. And these are the parameters we obtained for this, in this case, heat capacity and heat transfer coefficient. The values obtained are close to the ones reported in the literature and the ones we have measured by independent means. This is basically what it does is corroborates the validity of the model and essentially the assumption that we made that only the particles that are in the cross section between the beam and the sample are the ones that produce heat. In the second experiment, we also obtained similar results. The parameters converge to values that are reasonable between in the context of what we are analyzing. This is a polymer different from the previous case. And again, what it does is corroborates the validity of the model. Well, finally, I would like to put some conclusions. We have proposed a three-dimensional model that can be used to calculate the complete temperature map in a piece of material loaded with plasmonic nanoparticles and irradiated with laser light. The model is very appropriate to perform parameter and state estimation, control and optimization, something that we will try to do in the future. We have used the model to estimate thermal parameters, like the heat capacity and the heat diffusion coefficient, and in simulated, as well as in experimental examples, the ones I showed you in the last slides. And this, with the goal of reducing computational time for online and offline computation, we have proposed reduced models based on the assumption of infinite dimensionality in one or two of the three variables. We have checked the reduced models in their ability to recover the real parameters for the system through parameter estimation. Depending on the size of the illuminated area, the reduced models may recover or not reasonable values for the parameters. Some ideas were preliminarily analyzed in order to improve the capability of the reduced models to assess, through parameter estimation, the right parameters. We concluded that adding measurements at specific locations in the sample may help to reduce models, may help to make the reduced model more robust with respect to the ability to track the real parameters. Well, I think I am in time. Thank you very much.
Thank you.